Organic chemistry, some basic principles and the techniques. Now, after studying this unit, you will be able to understand reasons for the tetravalence of the carbon and the shape of the organic molecules, the right structure of the organic molecule in the various base, classify the organic compounds, name the compounds according to the IUPAC system of the nomenclature, and also derive their structure from the given names. Understand the concept of the organic reaction mechanism. Explain the influence of the electronic displacement on the structure and the reactivity of the organic compounds. Recognize the type of the organic reaction. Learn the techniques of the purification of the organic compounds. Write the chemical reaction involved in the qualitative analysis of the organic compounds. Understand the principles involved in the quantitative analysis of the organic compounds. Now, in the previous unit, you have learned that the element carbon has a unique property called the catenation, due to which it forms covalent bonds with other carbon atoms. It also forms covalent bonds with the atoms of the other elements like the hydrogen, oxygen, nitrogen, sulfur, and phosphorus, and halogens. The resulting compounds are studied under a separate branch of the chemistry called the organic chemistry. This unit incorporates some basic principles and the techniques of the analysis required for the understanding the formation and the properties of the organic compounds. General introduction. Organic compounds are vital for sustaining life on the earth and include complex molecules like the genetic information on bearing deoxyribonucleic acid, DNA, and proteins that constitute essential compounds of our blood, muscles, and skin. Organic compounds appear in materials like the clothing, shoes, polymers, dyes, and the medicines. These are some of the important areas of the application of these compounds. Science of the organic chemistry is about 200 years old. Around the year 2080, chemists began to distinguish between the organic compounds obtained from the plants and the animals and inorganic compounds prepared from the mineral sources. Berzelius, a Swedish chemist, proposed that vital forces were responsible for the formation of the organic compound. However, this notion was rejected in the 1828 when the F. Waller synthesized an organic compound urea from the inorganic compound ammonium cyanide. जैसे अमोनियम फाइनाइट NH4CnO को हीट करने पर यूरिया मिलता है और NH2 को NH2 यूरिया. The pioneering synthesis of the acetic acid by the Colby 1845 and that of the methane by the Berthollet 1858 showed conclusively that organic compounds could synthesized from the inorganic sources in the laboratory. The The development of the electronic theory of the covalent bonding ushered organic chemistry into its modern shape. Tetravalence of the carbon shapes of the organic compounds. The shapes of the carbon compound. The knowledge of the fundamental concept of the molecular structure helps in understanding and predicting the property of the organic compounds. You have already learned theories of the valency and the molecular structure in the unit 4. Also, you already know the tetravalence of the carbon and the formation of the covalent bonds. By it are explained in the terms of the electronic configuration and the hybridization of the s and the p orbitals. It may be recalled that the formation and the shapes of the molecules like the methane CH4, ethane C2H4, and the ethane C2H2 are explained in the terms of the use of the sp3, sp2, and the sp hybrid orbitals by the carbon atoms in the respective molecules. Hybridization influences the bond length and the bond enthalpy of strength in the compounds. The sp hybrid orbitals contains more s character and hence it is close to the nucleus and forms shorter and stronger bonds than the sp3 hybrid orbitals. The sp2 hybrid orbitals is intermediate in the s character between the sp and the sp3 and hence the length and the enthalpy of the bond it forms are also intermediate between them. The change in the hybridization affects the electronegativity of the carbon. The greater the s character in the hybrid orbitals, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50% s character is more electronegative than that possessing sp2 or the sp3 hybridized orbitals. This relative electronegativity is reflected in the several physical and the chemical properties of the molecule concerned, and about which we will learn in the later units. Some characteristic features of the pi bonds. In a pi bond formation, parallel orientation of the two p orbitals on adjacent atom is necessary for a proper sidewise overlap. thus in the C2 double bond C2 molecule, all the atoms must be in the same plane. The p orbitals are mutually parallel, and both the p orbitals are perpendicular to the plane of the molecule. Rotation of the one C2 fragment with respect to the other interferes with the maximum overlap of the p orbitals, and therefore such rotation about the carbon-carbon double bond C is restricted. The electron charge cloud of the pi bond is located above and below the plane of the bonding atoms. This results in the electron being easily available to the attacking reagents. In general, pi bonds provide the most reactive centers in the molecule containing the multiple bonds. Now problem 12.1, how many sigma and the pi bonds are present in each of the following molecule? पहला है कि CH ट्रिपल बॉन्ड CH डबल बॉन्ड CH3 और दूसरा CH2 डबल बॉन्ड फिर डबल बॉन्ड CH और फिर CH3। तो इसमें सिग्मा CC4 और सिग्मा CH6, पाई CC1 और पाई CC2, फिर सिग्मा CC3, सिग्मा CH6 और पाई C डबल बॉन्ड C2 है। फिर आता है प्रॉब्लम की भाटी द टाइप ऑफ द हाइब्रिडेशन ऑफ द ईच कार्बन इन द फॉलोइंग कंपाउंड CH3Cl, sp3 CH3 2CO, sp3 और sp2 है, फिर C3CN में sp3 और sp है, फिर HUONH2 में D में sp2 है और C3CH डबल बॉन्ड CHCN में sp3 sp2 और sp है। Now the problem 12.3, write the state of the hybridization of the carbon in the following compound and shape of each of the molecule। जैसे CH2 डबल बॉन्ड O और C3F और CHN में sp3 हाइब्रिडाइड कार्बन है ट्रायगोनल प्लेनर, sp3 हाइब्रिडाइड कार्बन टेट्राहेड्रल और sp हाइब्रिडाइड कार्बन लीनियर है। फिर आता है स्ट्रक्चर रिप्रेजेंटेशन ऑफ द ऑर्गेनिक कंपाउंड्स। The structures of the organic compounds are represented in the several ways. The Lewis structure of the dot structure, dash structure, condensation structure, and bond line structure formulas are some of the specific type. The Lewis structure, however, can be simplified by representing the two electron covalent bond by a dash. Such a structural formula focus on the electrons involved in the bond formation. A single dash represents a single bond, double dash is used for the double bond, and a triple dash represents triple bond. Lone pair of the electrons on the heteroatoms, example oxygen, nitrogen, sulfur, halogen, etc., may or may not be found. Thus, the ethane C2H6, ethene C2H4, and the ethine C2H2, and the methanol CH3OH can be represented by the following structural formula. Such structural representations are called the complete structure formula। जैसे इथेन हो गया, इथीन हो गया, इथाइन हो गया और मिथेनॉल हो गया। These structural formula can be further abbreviated by omitting some or all of the dashes representing covalent bonds and by indicating the number of the identical groups attached to an atom or by a subscript. The resulting expression of the compound is called the condensed structure formula. Thus, ethane, ethine, and the methanol can be written as ethane, फिर ethene, ethine और methanol। Similarly, CH3, CH2, 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 CH3 can be further condensed as CH3, CH2, 6 or CH3. For further simplification, organic chemists use another way of representing the structure in which only lines are used. In this bond line structure representation of the organic compounds, carbon and hydrogen atoms are not shown and the lines representing carbon-carbon bonds are drawn in a zigzag fashion. The only atoms officially written are the oxygen, chlorine, nitrogen, etc. The terminals denote methyl C3 group unless indicated otherwise a functional group, while the line junctions denote carbon atoms bonded to the appropriate number of the hydrogen required to satisfy the balance of the carbon atoms. Some of the examples are represented as follows. 3-methyl octane can be represented in the various forms as CH3 CH2 CH, फिर CH2 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 C3 और C3 हो गया। उसके बाद फिर आता है ये इस तरह से भी कर सकते हैं और टर्मिनल्स ग्रुप्स को इस तरह से मिसाल कर सकते हैं। उसके बाद फिर आता है वेरियस वेज ऑफ रिप्रेजेंटिंग 2 ब्रोमोब्यूटेन आर। एक तो ये तरीका हो गया, फिर इस तरीके से भी कर सकते हैं और फिर बॉन्ड लाइन से डायरेक्ट भी कर सकते हैं। फिर आता है कि इन द साइक्लिक कंपाउंड्स द बॉन्ड लाइन फार्मूला मे बी गिवन एज कि साइक्लोप्रोपेन हो गया, फिर साइक्लोपेंटेन हो गया और साइक्लोहेक्सेन हेक्सेन हो गया, जिसको बॉन्ड लाइन से डायरेक्टली ऐसे दिखा सकते हैं। एक्सपैंड ईच ऑफ द फॉलोइंग कंडेंसड फार्मूला इनटू देयर कंप्लीट स्ट्रक्चर फार्मूला, जैसे CH3 C2 CO C2 C3 हो गया, और C3 CH डबल बॉन्ड CH C2 के 3 और CH3 है, तो इसको एक्सपैंड कर सकते हैं इस तरह से और इस तरह से। फिर आता है प्रॉब्लम 12.5 कि फॉर ईच ऑफ द फॉलोइंग कंपाउंड्स राइट ए कंडेंसड फार्मूला एंड अल्सो देयर बॉन्ड लाइन फार्मूला। तो आता है OH C2 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 CH C3 CH C3 और CH3 ये है, इसको दिखाने के लिए इस तरफ से, और बी में इसको दिखाने के लिए कंडेंसेशन फार्मूला इसका हो सकता है ये और ये, फिर बॉन्ड लाइन फार्मूला इसका इस तरफ से और इस तरफ से कर सकते हैं। फिर आता है एक्सपैंड ईच ऑफ द फॉलोइंग बॉन्ड लाइन फार्मूला टू शो ऑल द एटम्स इंक्लूडिंग द कार्बन एंड द हाइड्रोजन। इसका 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 तो सॉल्यूशन है, इसका दिया हुआ है, इसका इसका इस तरफ से, फिर इस तरफ से, इस तरफ से और इस तरफ से फिर हम दिखा सकते हैं। फिर उसके बाद आता है 3 डायमेंशनल representation of the organic molecule. The three-dimensional representation, 3D structure of the organic molecules can be represented on the paper by using the certain convention. For example, using solid and a daffed wedge formula. Solid and a daffed wedge formula, the 3D image of a molecule form a two-dimensional picture can be perceived. In this formula, the solid wedge is used to indicate a bond projecting out of the paper towards the observer. The daffed wedge is used to depict the bond projecting out of the plane of the paper and away from the observer. Wedges are shown in such a way that the broad end of the wedge is towards the observer, the bond lying in the plane of the paper, and depicted by using a normal plane 3D representation of the methane molecule on the paper has been shown in the figure 12.1. The bonds in the plane of the paper और डैफेड बेज फ्रॉम द ऑब्जर्वर, और इधर हो गया सॉलिड बॉन्ड्स टुवर्ड्स द ऑब्जर्वर और बेज एंड द डेफ रेपिटेशन ऑफ द CH4। फिर मॉलिकुलर मॉडल्स आर फिजिकल डिवाइसेज दैट आर यूज्ड फॉर ए बेटर विजुअलाइजेशन एंड परसेप्शन ऑफ द थ्री डायमेंशनल शेप्स ऑफ द ऑर्गेनिक molecules. These are made up of wood, plastic, or the metal and are commercially available. Commonly, three types of the molecule models are used, जैसे framework model, ball and stick model, space filling model. In the framework model, only the bond connecting the atom of a molecule are not the atom themselves are shown. This model emphasizes the pattern of the bonds of a molecule while ignoring the size of the atom. In the ball and stick model, both the atoms and the bonds are shown. Balls represent atoms and the stick denotes a bond compound containing the C. Ethene can be best represented by using the springs in the place of the sticks. These models are referred to as the ball and the spring model. The space filling model emphasizes the relative size of each atom based on its van der Waals radius. Bonds are not shown in this model. It conveys the volume occupied by each atom in the molecule. In addition to these models, computer graphics can also be used for the molecular modeling. Now the framework model and the ball and the stick model and the space filling model. Classification of the organic compounds. The existing large number of the organic compounds and their ever-increasing numbers has made it necessary to classify them on the basis of their structure. Organic compounds are broadly classified as follow. पहले ऑर्गेनिक कंपाउंड्स को एसाइक्लिक और द ओपन चेन कंपाउंड्स में, फिर साइक्लिक और द क्लोज चेन और द रिंग कंपाउंड्स में, फिर रिंग और द क्लोज चेन और द रिंग कंपाउंड्स को एलिसाइक्लिक और एरोमेटिक कंपाउंड्स में, एलिसाइक्लिक को होमोसाइक्लिक और द कार्बोसाइक्लिक कंपाउंड्स में, और एलिसाइक्लिक को ही हेट्रोसाइक्लिक कंपाउंड्स जिसे नॉन एरोमेटिक कहते हैं। फिर एरोमेटिक कंपाउंड्स को बेंजीनॉइड कंपाउंड्स में और नॉन बेंजीनॉइड कंपाउंड्स में और हेट्रोसाइक्लिक एरोमेटिक कंपाउंड्स में डिवाइड किए हैं। तो aliphatic or the open chain compounds. These compounds are also called the aliphatic compounds and consist of the straight or the branch chained compounds. For example, जैसे इथेन हो गया, फिर आइसोब्यूटेन हो गया, एसिटाल्डिहाइड और द एसिटिक एसिड हो गया। उसके बाद फिर द साइक्लिक और द क्लोज चेन और द रिंग कंपाउंड्स, एलिफैक्लिक कंपाउंड्स। एलिफैटिक compounds contain carbon atoms joined in the form of the ring, जैसे साइक्लोप्रोपेन, साइक्लोहेक्सेन इस तरह से। समटाइम्स other, sometimes atoms other than the carbon are also present in the rings. Heterocyclic tetrahydrofuran given below is an example of this type of the compound. It's a tetrahydrofuran. These exhibit some of the properties similar to those of the aliphatic compounds. Aromatic compounds. Aromatic compounds are the special type of the compounds. We will learn about these compounds in detail in the unit 13. These include benzene and the other related ring compounds, benzenoid. Like aliphatic compounds, aromatic compounds may also have heterocompounds atom in the ring. Such compounds are called heterocyclic aromatic compounds. Some of the examples of the various types of the aromatic compounds are, एक तो हो गया बेंजीन, फिर एनिलीन और द नैप्थलीन, फिर नॉन बेंजीनॉइड कंपाउंड में आता है ट्रोपोन। उसके बाद फिर हेट्रोसाइक्लिक एरोमेटिक कंपाउंड्स में फ्यूरन, फिर थायोफिन और पैरिडीन आते हैं। Organic compounds can also be classified on the basis of the functional group into families or the homologous series. Now the functional groups. The functional group is an atom or a group of the atom joined to a carbon chain which is responsible for the characteristic chemical property of the organic compound. The examples are the hydroxyl group OH, aldehyde group CHO, and the carboxylic acid group COOH, etc. Homologous series, a group or a series of the organic compounds each containing a characteristic functional group forms a homologous series, and the members of the series are called the homologues. The members of the homologous series can be represented by general formula, molecular formula, and the successive members differ from each other in its molecular formula by the fixed unit. There are a number of the homologous series of the organic compounds. Some of these are the alkanes, alkenes, alkynes, haloalkanes, alkanols, alkanals, alkanones, alkanic acid, amines, etc. It is also possible that a compound contains two or more identical or different functional groups. This gives to the polyfunctional compound. Now the nomenclature of the organic compounds. The organic chemistry deals with millions of compounds. In order to clearly identify, a systematic method of naming has been developed and is known as the IUPAC, International Union of Pure and the Applied Chemistry System of the Nomenclature. In the systematic nomenclature, the names are correlated with the structure such that the reader or the listener can deduce the structure from the name. Before the IUPAC system of the nomenclature, however, organic compounds were assigned names based on their origin or the certain property. For instance, citric acid is named so because it is found in the citrus fruits, and the acid found in the red ant is from formic acid, since the Latin word for the and is the formica. These names are traditional and are considered either trivial or the common names. Some common examples are followed even today. For example, Buckminster fullerene is the common name given to the newly discovered C60 cluster, a form of the carbon, noting its structural similarity to the geodesic domes popularized by the famous architect R. Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematic names are lengthy and complicated. Common names of the some organic compounds are given in a table 12.1. Now the CH4 methane, CH2 CH2 CH3 CH3 N-butane, or CH3K2 CH3 isobutane, CH4 C neopentane, or CH2 CH2 OH CH3 N propyl alcohol, HCHO formaldehyde, CH3 2-CO-acetone, or CHCl3 chloroform, CH3-phenol-OH acetic acid, C6H6 benzene, C6H5 OC3-anisole, C6H5NH2 aniline, or C6H5CONH3 acetophenone, फिर CH3O CH2 CH3 ethyl methyl ether हो गया. The IUPAC system. The IUPAC system of the nomenclature, a systematic name of an organic compound, is generally derived by identifying the parent hydrocarbon and the functional group attached to it. See the example given below. Now, by further using prefix and the suffix, the parent name can be modified to obtain the actual name. Compounds containing carbon and the hydrogen only are called the hydrocarbons. A hydrocarbon is termed saturated if it contains only carbon-carbon single bond. The IUPAC name for a homologous series of the such compounds is alkane, paraffin, Latin little affinity. By the earlier name given to these compounds, unsaturated hydrocarbons are those which contain at least one carbon double, or the triple bond. Now the IUPAC nomenclature of the alkanes. Of straight chain hydrocarbon, the names of such compounds are based on their chain structure and it with the suffix "-n" and carry a prefix indicating the number of the carbon atom present in the chain except for the CH4 to CH4H10 where the prefixes are derived from the trivial names. The IUPAC name of the some straight chain saturated hydrocarbons are given in table 12.2. The alkanes in table 12.2 differ from each other by merely the number of the C2 groups in the chain. They are homologous of the alkane series. Now the IUPAC name of the some unbranched saturated hydrocarbons. The branched chain hydrocarbons in a branched chain compound, small chains of carbon atoms are attached at one or more carbon atoms of the parent chain. The small carbon chain branches are called the alkyl group. For example CH2 CH3 CH CH2 CH2 और ये यहाँ पर एक है, एक यहाँ पर है. उसके बाद फिर अगर मीथेन है तो CH4 और इथेन है तो C2H6, प्रोपेन तो C3H8, 4 है तो ब्यूटेन, 5 है तो पेंटेन, 6 है तो हेक्सेन, 7 है तो हेप्टेन, 8 है तो ऑक्टेन, 9 है तो नॉनेन, 10 है तो डेकेन, 20 है तो आइसोकेन और अगर 30 है तो ट्राया कॉन्टाने C30H12. उसके बाद फिर आता है in order to name such compounds, the names of the alkyl groups are prefixed to the name of the parent alkane. An alkyl group is derived from a saturated hydrocarbon by removing a hydrogen from the atom. Thus CH4 becomes CH3 and is called the methyl group. And alkyl group is named by substituting YL for the N, and in the corresponding alkane some alkyl groups are listed in table 12.3. जैसे मीथेन CH4 हो गया, इथेन C2H6 हो गया, प्रोपेन C3H8 हो गया, ब्यूटेन C4H10 हो गया और डिकेन C10H22 हो गया. फिर मिथाइल हो गया ये, फिर इथाइल हो गया ये, प्रोपाइल हो गया ये, ब्यूटाइल हो गया ये और डेकाइल हो गया ये. Abbreviations are used for some alkyl groups. For example, methyl is abbreviated as the Me, ethyl as the Et, propyl as the Pr, and butyl as the Bu. The alkyl groups can be branched also, thus propyl and the butyl groups can have branched structure as shown below. जैसे isopropyl, फिर sec butyl, isobutyl, फिर tert butyl और neopentyl. Common branched group have a specific trivial names. For example, the propyl group can either be N-propyl group or the isopropyl group. The branched butyl groups are called sec butyl, isobutyl, and the tert butyl group. We also encounter the structure unit CH2CH3K3, which is called the neopentyl group. Now the nomenclature of the branched chain alkanes. We encounter a number of the branched chain alkanes. The rules for naming them are given below. सबसे पहले आता है if first of all the longest carbon chain in the molecule is identified. In the example given below, the longest chain had the 9 carbon and it is considered as the parent or the root chain. So selection of the parent chain as is shown in the 2 is not correct because it has only 8 chains. दूसरा the नॉट करेक्ट, तो ये वाला सही है और ये है जो गलत है. दूसरा कि द कार्बन एटम्स ऑफ द पेरेंट चेन आर नंबर्ड टू आइडेंटिफाई द पेरेंट अल्केन एंड टू लोकेट द पोजीशन ऑफ द कार्बन एटम्स at which the branching takes place due to the substitution of the alkyl group in the place of the hydrogen atom. The numbering is done in such a way that the branched carbon atoms get the lowest possible number. Thus the numbering in the above example should be from the left to right, branching at the carbon from 2 to 6 and not from the right to left, giving numbers 4 and 8 to the कार्बन एटम्स एट विच द ब्रांचेज आर अटैचड. तो ये हो गया और ये हो गया. उसके बाद फिर आता है द तीसरा द नेम्स ऑफ द अल्काइल ग्रुप अटैचड एज ए ब्रांच आर देन प्रीफिक्स्ड टू द नेम ऑफ द पेरेंट अल्केन एंड पोजीशन ऑफ द सब्स्टिट्यूएंट इज इंडिकेटेड बाय द एप्रोप्रिएट नंबर. इफ डिफरेंट अल्काइल ग्रुप्स आर प्रेजेंट दे आर लिस्टेड इन अल्फाबेटिकल ऑर्डर. दस द नेम फॉर द कंपाउंड शोन अबव इज द 6 ethyl 2 methyl nonane. Note the number are separated from the group by hyphens and there is no break between the methyl and the nonane. चौथा कि if two or more identical substituent groups are present then the numbers are separated by comma. The names of the identical substituents are not repeated. Instead prefixes such as the di or the 2, tri or the 3 or tetra or the 4 or penta or the 5, hexa for the 6 etc. are used. By writing the name of the substituent in the alphabetical order, these prefixes however are not considered. Thus the following compounds are named as और 2,2,4 डाईमिथाइल पेंटेन, और इसका कर सकते हैं 2,2,4 ट्राईमिथाइल पेंटेन, और इसका कर सकते हैं 3 इथाइल 4,4 डाईमिथाइल हेप्टेन। नाउ पचमा है कि इफ द two equivalent substituents are found in the equivalent position, the lower number is given to the one coming first in the alphabetical listing. Thus, the following compound is 3-ethyl 6-methyl octane and not 6-ethyl 3-methyl octane. The branched alkyl groups can be named by following the above-mentioned procedure. However, the carbon atom of the branch that attached to the root alkane is numbered 1 is exemplified below. तो इसका नाम हो सकता है 1,3-डाईमिथाइल ब्यूटाइल। उसके बाद फिर आता है कि the name of the first branched chain alkyl group is placed in a parenthesis while naming the compound. While writing the trivial names of the substituent in alphabetical order, the prefix iso and the neo are considered to be the part of the fundamental name of the alkyl group. The prefix sec and the tert are not considered to be the part of the fundamental name. The use of the iso and the related common prefixes for naming the alkyl group should also be allowed by the IUPAC nomenclature as long as these are not further substituted. In the multi-substituted compounds, the following rules may also be remembered. पहला कि if there happens to be two chains of the equal phi, then that chain is to be selected which contains more number of the phi chain. After selection of the chain, numbering is to be done from the end closer to the substituent. तो इसका नेम हो जाएगा 5,2-ethyl butyl 3,3-dimethyl decane and not 5,2,2 diethyl butyl 3-ethyl decanane. उसका हो जाएगा 5-sec butyl 4 isopropyl decane और इसका हो जाएगा 5,2,2 dimethyl propyl nonene. Now the cyclic compounds. A saturated monocyclic compound is named as by prefixing cyclo to the corresponding substrate chain alkane. If the phi chains are present, then the rules given above are applied. Some name of the some cyclic compounds are given below. पहला हो गया cyclopentane, फिर आ गया 1-methyl 3-cyclopropyl hexane, फिर alphabetical order of the numbering, और फिर more branched carbon gets the lower number, और इधर 3-ethyl 1,1-dimethyl cyclohexane, not 1-ethyl 3,3-dimethyl cyclohexane. उसके बाद structure and the IUPAC names of the some hydrocarbons are given below. Explain why the names given in the parentheses are incorrect. तो इसमें आता है 2,5,6 ट्राईमिथाइल ऑक्टेन एंड नॉट 3,4,7 ट्राईमिथाइल ऑक्टेन, फिर इधर 3-ethyl 5-methyl हेप्टेन एंड नॉट 3-ethyl 3-methyl हेप्टेन. तो इसका सॉल्यूशन है कि लोएस्ट लोकेंट रूल number 256 is lower than the 357. Substituents are in the equivalent position. Lower number is given to the one that comes first in the name according to the alphabetical order. Now the nomenclature of the organic compounds having functional group. A functional group is identified earlier in an atom or a group or atom bonded together in a unique manner, which is usually the site of the chemical reactivity in an organic molecule. Compounds having the same functional group undergo similar reaction. For example, CH3OH, CH3CH2OH and the CH3K2CHOH, all having OH functional group, liberate hydrogen or on reaction with a sodium metal. The presence of the functional group enables systematization of the organic compounds into different classes. Examples of some functional group with their prefixes and the suffix along with some example of the organic compounds present. These are given in the table 12.4. First of all, the functional group present in the molecule is identified, which determines the choice of the appropriate suffix. The longest chain of the carbon atoms containing the functional group is numbered in such a way that the functional group is attached at the carbon atom possessing lowest possible number in the chain. By using the suffix as given in table 12.4, the name of the compound is arrived at. In the case of the polyfunctional compounds, one of the functional group is chosen as the principal functional group and the compound is then named on that basis. The remaining functional group, which are subordinate functional group, are named as the substituent using the appropriate prefix. The choice of the principal functional group is made on the basis of the order of the preference. The order of the decreasing priority for the some functional group are सबसे ज़्यादा फिडोल-OH, उससे कम FO3H, उससे कम फिडोल-OR, फिर COCl, फिर ONH2, CN, फिर फिर डबल-OH, फिर डबल बॉन्ड O, फिर OH NH2, फिर डबल बॉन्ड C और फिर ट्रिपल बॉन्ड C. इधर से लिख सकते हैं कि सबसे ज़्यादा COOH फिर उसके बाद आता है FO3H, फिर आता है फिडोल OR, फिर आता है FuCl, फिर आता है FeONH2 और फिर आता है Pn, फिर आता है H डबल बॉन्ड O, उसके बाद आता है Phi डबल बॉन्ड O, फिर आता है OH, फिर आता है NH2 और फिर आता है Phi डबल बॉन्ड C और फिर आता है Phi ट्रिपल बॉन्ड C. The R6H5 halogens, polychlorine, bromine, iodine, NO2, oxy, OR, etc. are always prefix substituent. Thus, a compound containing both an alcohol and a keto group is named as the hydroxyalkone since the keto group is preferred to the hydroxyl group. For example, OH, C2, C3, C2, phenol O, C3 will be named as 7-hydroxyheptane 2-on and not as the 2-oxoheptane phenol. Similarly, Br2CH2 is named as 3-bromoprop 1-in and not 1-bromoprop 2-in. If more than one functional group of the same type are present, their number is indicated by adding di, tri, etc. before the class suffix. In such cases, the full name of the parent alkane is written before the class suffix. For example, CH2OH is named as ethane 1,2-diol. However, the ending "in" of the parent alkane is dropped in the case of the compound having more than one double or the triple bond. For example, CH2 double bond CH plus single CH double bond CH2 is named as buta-1,3-diene. Now, write the IUPAC name of the compounds 1 to 4 from the given structure. तो पहला, the functional group present in an alcohol OH, hence the suffix is OL. The longest chain containing OH has 8 carbon atoms, hence the corresponding saturated hydrocarbon is the octane. The OH is on carbon atom 3. In addition, the methyl group is attached at the 6th carbon, hence the systematic name of the compound is 6-methyl-octane-3-OL. उसके बाद फिर सॉल्यूशन दूसरा का कि द सॉल्यूशन द फंक्शनल ग्रुप प्रेजेंट इज द कीटोन, hence suffix on presence of the two keto groups is indicated by the dry, hence the suffix becomes dione. The two keto groups are at the carbon 2 and 4. The longest chain contains the 6 carbon atoms, hence the parent hydrocarbon is the hexane. Thus, at the systematic name is the hexane 2,4-dione. Now the functional group of structure. IUPAC group of structure, IUPAC group suffix and examples. जैसे alkanes का हो गया butenes, alkenes का हो गया but1-in, alkanes का हो गया but1-ine, arenes का हो गया benzene, halides का हो गया halo-1-bromobutane, alcohols का हो गया hydroxy butane 2-ol, aldehydes का हो गया formyl और the oxo-butanal और the ketones का हो गया oxo-1 butane 2-1, nitriles का हो गया phenol-1-n, फिर ethers का हो गया ROR, फिर कार्बोक्सिलिक एसिड का हो गया फिडोल-OH, कार्बोक्सिलेट आयन का हो गया फिडोल-O-, ईस्टर का हो गया फिडोल-OR, एफाइल एल्डिहाइड्स का हो गया FeOX, एमाइन्स का हो गया NH2, एमाइड्स का हो गया FeONH2, FeONHR, FeONR2, नाइट्रो का हो गया NO2 और सल्फोनिक एसिड का हो गया FO3H. नाउ द सॉल्यूशन तीसरा वाला का कि here the two functional group namely the ketone and the carboxylic acid are present. The principal functional group is at the carboxylic acid group, hence the parent chain will be suffixed with the oic acid. Numbering of the chain starts from the carbon of the phenol-OH functional group. The keto group of the chain at the carbon 5 is indicated by the oxo. The longest chain including the principal functional group has the 6 carbon atom, hence the parent hydrocarbon is hexane. The compound is therefore named as the 5-oxohexanoic acid. फिर सॉल्यूशन है इसका वाला का कि the two phenol-C functional groups are present at the carbon atom 1 and 3 while the triple bond C functional group is present at the carbon 5. These groups are indicated by the suffix diene and the ene respectively. The longest chain containing the functional groups has the 6 carbon atoms, hence the parent hydrocarbon is the hexane. The name of the compound therefore is the hexa-1,3-diene 5-ene. Now the problem 12.9 derive the structure of the 2-chlorohexane pent 4En2 2 pent 4En2OL nitrocyclohexane cyclohex 2En1OL and the 6-hydroxyheptanol. The solution key hexane indicates the presence of the 6 carbon atoms in this chain. The functional group of the chloro is present. The functional group of the chloro is present at the carbon 2, hence the structure of the compound is C3CH2CH2CH2 CHCl3, or the pent indicates the parent hydrocarbon contains 5 carbon atoms in the chain. En and the OL correspond to the functional group C and the OH at the carbon atoms 4 and 2 respectively. Thus the structure is CH2CH, CH2CH, OH, CH3. Now the fixed-membered ring containing a carbon-carbon double bond is employed by the cyclohexane, which is numbered as the shown in the 2. The prefix 3 nitro means that a nitro group is present on the C3. Thus, the complete structure formula of the compound is 2. Double bond is suffixed functional group, whereas NO2 is prefixed functional group. Therefore, the double bond has the get preference over the NO2 group. 1OL means that an OH group is present at the C1. OH is suffixed functional group and gets preference over the C double bond C bond. Thus, the structure is shown in the 2. Now the heptanol indicates the compound to be an aldehyde containing 7 carbon atom in the parent chain. The 6-hydroxy indicates that the OH group is present at the carbon 6. Thus the structural formula of the compound is CH3CHOH2 CH2CH2CH2CHO. Carbon atom of the CHO group is included while numbering of the carbon chain. Now the nomenclature of the substituted benzene compound. For the IUPAC nomenclature of the substituted benzene compounds, the substituent is placed as the prefix to the word benzene as shown in the following example. However, common names written in the bracket below of many substituted benzene compounds are also universally used. तो मिथाइल बेंजीन को हम कह सकते हैं टोलिन, मिथॉक्सी बेंजीन को कहते हैं एनिफोल और द अमीनो बेंजीन को कहते हैं एनिलीन, फिर नाइट्रो बेंजीन को कहते हैं एक हो गया इधर ब्रोमोबेंजीन. If the benzene ring is disubstituted, the position of the substituent is the position of the disubstituent is defined by numbering the carbon atoms of the ring such that the substituents are located at the lowest number possible. For example, the compound is named as the 1,3-dibromobenzene and not as the 1,5-dibromobenzene. तो 1,2-dibromobenzene, 1,3-dibromobenzene और 1,4-dibromobenzene ये हो गया. In the trivial system of the nomenclature, the term ortho, meta, and the para are used as prefix to indicate the relative position of the 1, 2, 1, 3, and the 1, 4 respectively. Thus, the 1,3-dibromobenzene is named as meta-dibromobenzene. Meta is abbreviated as the M, and the other isomers of the dibromobenzene 1, 2, A and the 1,4-C are named as the ortho or just ortho and the para or just para dibromobenzene respectively. For the tri or the higher substituted benzene derivatives, this prefix cannot be used and the compounds are named by identifying substituent position on the right ring by following the lowest locant rule. In some cases, the common name of the benzene derivative is taken as the base compound. So, substituent of the base compound in the assigned number 1 and then the direction of the numbering is chosen such that the next substituent get the lowest number. The substituent appears in the name in the alphabetical order. Some examples are given below. जैसे 1-chloro 2,4-dinitrobenzene not 4-chloro 1,3-dinitrobenzene. फिर 2-chloro 1-methyl 4-nitrobenzene not 4-methyl 5-chloro nitrobenzene. फिर 2-chloro 4-methyl anisole और 4-ethyl 2-methyl aniline. फिर 3,4-dimethyl phenol. उसके बाद when a benzene ring is attached to an alkane with a functional group, it is considered as substituent instead of a parent. The name of the benzene as the substituent is phenyl C6H5, also abbreviated as the phenyl. Now write the problem 12.10. Write the structure formula of the ortho-ethyl anisole, para-nitroaniline, 2,3-dibromo 1-phenylpentane and the 4-ethyl 1-fluoro 2-nitrobenzene. इसमें ये आ जाता है, फिर ये आता है NHNO2, फिर इसमें का ये हो जाएगा और इसका ये हो जाएगा. Now the isomerism. The phenomena of the existence of two or more compounds possessing the same molecular formula but different property is known as the isomerism. Such compounds are called as the isomers. The following chart shows different types of the isomerism. A structural isomerism: compounds having the same molecular formula but different structure manners in which the atoms are linked are classified as the structural isomer. Or some typical examples of the different types of the structural isomers are given below. Chain isomerism: when two or the more compounds have the similar molecular formula but different carbon skeleton. These are referred to as the chain isomer, and the phenomena is termed as the chain isomerism. For example, C5H12 depends the compound. उसको आ जाता है पेंटेन, इधर आ गया आइसोपेंटेन 2 मिथाइल ब्यूटेन, और इधर आ गया नियोपेंटेन 2 डाइमिथाइल प्रोपेन का. फिर आता है पोजीशन आइसोमेरिज्म कि the when two or more compounds differ in the position of a substituent atom or the functional group of the carbon skeleton, they are called the position isomers, and this phenomena is termed as the position isomerism. For example, the molecular formula C3H8O represents the 2 अल्कोहल, तो प्रोपेन 1 ओल का ये हो जाएगा और प्रोपेन 2 ओल तो यहाँ पर आ जाएगा. अब आता है ये दोनों है जो पोजीशन आइसोमेरिज्म है. फिर आता है फंक्शनल आइसोमेरिज्म. Two or more compounds having the same molecular formula but different functional groups are called the functional isomers, and this phenomena is termed as the functional group isomerism. For example, the molecular formula of the C3H6O represents the aldehyde and the ketone. तो प्रोपेनॉन और प्रोपेनॉल ये दोनों फंक्शनल आइसोमेरिज्म है. नाउ द मेटामेरिज्म, it arises due to the different alkyl chains on the either side of the functional group in the molecule. For example, C4H10O represents the methoxypropane, C3O C3C7 and the ethoxyethane, C2H5O C2H5. ये दोनों मेटामर्स हैं. तो आइसोमेरिज्म को हम डिवाइड कर सकते हैं स्ट्रक्चरल आइसोमेरिज्म में और स्टीरियो आइसोमेरिज्म. फिर स्ट्रक्चरल आइसोमेरिज्म को चेन आइसोमेरिज्म, पोजिशनल आइसोमेरिज्म, फंक्शनल ग्रुप आइसोमेरिज्म और मेटामेरिज्म में, और स्टीरियो आइसोमेरिज्म को ज्योमेट्रिकल आइसोमेरिज्म और फिर उसको ऑप्टिकल आइसोमेरिज्म में कर सकते हैं. फिर आता है स्टीरियो आइसोमेरिज्म. तो the compounds that have the same constitution and sequence of the covalent bonds but differ in the relative position of their atoms or the groups in the space are called the stereoisomers. This special type of the isomerism is called as the stereoisomerism and can be classified as the geometrical and the optical isomerism. Fundamental concepts in the organic reaction mechanism. In an organic reaction, the organic molecule, also referred as the substrate, reacts with an appropriate attacking reagent and can lead to the formation of one or more intermediate and finally products. The general reaction is depicted as follow कि सबसे पहले ऑर्गेनिक मॉलिक्यूल सबस्ट्रेट अटैकिंग रिएजेंट, फिर इंटरमीडिएट और प्रोडक्ट्स और बाई प्रोडक्ट्स बन गए. Substrate is that reactant which supply carbon to the new bond and the other reactant is called the reagent. If both the reactants supply carbon to the new bond, then choice is arbitrary, and in that case the molecule on which attention is focused is called as the substrate. In such a reaction, a covalent bond between the two carbon atom or a carbon and some other atom is broken and new bond is formed. A sequential account of each step describing details of the electron movement, energetics during the bond cleavage and bond formation, and the rate of the transformation of the reactants into products kinetics is referred to as the reaction mechanism. The knowledge of the reaction mechanism helps in understanding of the reactivity of the organic compounds and in planning a strategy of their synthesis. In the following section, we shall learn some of the principles that explain how these reactions take place. Now, the fusion of a covalent bond. A covalent bond can get cleaved either by the heterolytic cleavage or by the homolytic cleavage. In the heterolytic cleavage, the bond breaks in such a fashion that the shared pair of the electron remains with one of the fragments. After heterolysis, one atom has a sextate electronic configuration and a positive charge, and the other a valence octet with at least one lone pair and a negative charge. Thus, heterolytic cleavage of the bromomethane will give C3 and the Br minus as shown below. A species having a carbon atom possessing sextate of the electrons and a positive charge is called a carbocation, earlier called the carbonium ion. The C3 plus ion is known as the methyl cation or the methyl carbonium ion. Carbocations are classified as the primary, secondary, or the tertiary, depending on whether 1, 2, or the 3 carbons are directly attached to the positively charged carbon. Some other examples of the carbocations are the C3C2 plus ethyl cation, a primary carbocation, C3 2 switch plus isopropyl cation, a secondary carbocation, and C3,3C plus terbutyl cation, a tertiary carbocation. Carbocations are highly unstable and reactive species. Alkyl groups directly attached to the positively charged carbon stabilize the carbocations due to the inductive and the hyperconjugation effect, which you will studying this in the section 12.1.5 and 12.1.9. The observed order of the carbocation stability is the C3 plus से ज़्यादा C2 C3 C2 मतलब 2 डिग्री मतलब वो फिर मिथाइल फिर 1 डिग्री फिर 2 डिग्री और सबसे ज़्यादा 3 डिग्री. These carbocations have trigonal planar shape with positively charged carbon being sp2 hybridized. Thus, the shape of the C3 plus may be considered as being derived from the overlap of the three equivalent C carbon sp2 hybridized orbitals. With 1s orbital of each of the three hydrogen atoms, each bond may be represented as C sp2h1 sigma bond. The remaining carbon orbital is perpendicular to the molecular plane and contain no electrons. The shape of the methyl carbocation, the heterolytic cleavage can also give a species in which carbon gets the shared pair of the electrons. For example, when group Z attached to the carbon leaves without electron pair, the methyl anion is formed. Such a carbon species carrying a negative charge on the carbon atom is called the carbon ion. Carbon in the carbon ion is generally sp3 hybridized and its structure is distorted tetrahedron as shown in the figure 12.3b. तो ये हो गया शेप ऑफ द मिथाइल कार्बोकेटाइन. और carbon ion are also unstable and reactive species. The organic reactions which proceed through the heterolytic bond cleavage are called the ionic or the heteropolar or just polar reaction. In the homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atoms. Thus, in the homolytic cleavage, the atom movement of a single electron takes place instead of a electron pair. The single electron movement is shown by the half-headed fish hook curved arrow. Such cleavage results in the formation of the neutral species atom or the group which contains an unpaired electron. These species are called the free radicals. Like the carbocations and the carbanions, free radicals are also very reactive. A homolytic cleavage can be shown as alkyl free radical. Alkyl radicals are classified as the primary, secondary, or the tertiary. Alkyl radical stability increases as we proceed from the primary to the tertiary. जैसे कि सबसे ज़्यादा थर्ड ब्यूटाइल रेडिकल, फिर आइसोप्रोपाइल फ्री रेडिकल, फिर इथाइल फ्री रेडिकल और इधर हो गया सबसे कम मिथाइल फ्री रेडिकल. उसके बाद फिर ऑर्गेनिक reactions which proceed by the homolytic fission are called the free radical or the homopolar or the non-polar reactions. Now the substrate or the reagents. Ions are generally not formed in the reactions of the organic compounds. Molecules as such participate in the reaction. It is convenient to name one reagent as substrate and the other as the reagent. In general, a molecule whose carbon is involved in the new bond formation is called the substrate and the other one is called the reagent. When carbon-carbon bond is formed, the choice of naming the reactant or as the substrate and the reagent is arbitrary and depends on the molecular under the observation. तो सबस्ट्रेट ये हो गया, रिएजेंट ये हो गया, तो प्रोडक्ट हमारा ये बन गया और फिर सबस्ट्रेट और रिएजेंट मिलकर हमारा प्रोडक्ट ये बना दिया. उसके बाद फिर आता है न्यूक्लियोफाइल्स एंड इलेक्ट्रोफाइल्स. रिएजेंट्स अटैक द रिएक्टिव पार्ट ऑफ द सबस्ट्रेट. द रिएक्टिव पार्ट में बी इलेक्ट्रॉन डिफिशिएंट. Electron deficient portion of the molecule, a positive reactive site. Example, an atom with incomplete electron shell or the positive end of the dipole in the molecule. If the attacking species is electron rich, it attacks this site. If the attacking species is electron deficient, the reactive site for it is that part of the substrate molecule which can supply electrons. Example, the pi electrons in a double bond. A reagent that brings an electron pair to the reactive site is called a nucleophile. That means nuclear seeking, and the reaction is called a nucleophilic. A reagent that takes away an electron pair from the reactive site is called the electrophile. The electron seeking and the reaction is called the electrophilic. During a polar organic reaction, a nucleophilic attacks an electrophilic center of the substrate, which is that specific atom or the part of the substrate which is electron deficient. Similarly, the electrophiles attack at the nucleophilic center, which is the electrons rich center of the substrate. Thus, the electrophiles receive electron pair from the substrate when the two undergo bonding interaction. A curved arrow notation is used to show the movement of an electron pair from the nucleophilic to the electrophile. Some examples of the nucleophile are the negatively charged ions with lone pair of electrons, such as the hydroxide ions, cyanide ions, and the carbon ions. Neutral molecules such as the H2O, R3N, R2NH, etc. can also act as the nucleophiles due to the presence of the lone pair of the electrons. Examples of the electrophiles include the carbocations and the neutral molecule having a functional group like the carbonyl group or the alkyl halides R3CX, where X is halogen atom. The carbon atom in the carbocation has state configuration, hence it is electron deficient and can receive a pair of the electrons from the nucleophiles. In the neutral molecules such as the alkyl halides, due to the polarity of the CX bond, a partial positive charge is generated on the carbon atom, and hence the carbon atom becomes an electrophilic center at which a nucleophile can attack. Now the problem 12.11, using the curved arrow notation show that the formation of the reactive intermediates when the following the covalent bond undergoes the heterolytic cleavage. तो C3 कैसे टूटेगा, फिर C3 कैसे टूटेगा और C3 कैसे टूटेगा. तो C3 टूटने का है C3 प्लस और C3 माइनस हो जाएगा. C3 टूटने का C3 प्लस और CN माइनस हो जाएगा और C3 के लिए C3 माइनस और C प्लस हो जाएगा. For giving justification, categorize the following molecule ion either nucleophilic or the electrophilic, जैसे HF minus PF3 C2H5O minus C3N or the Cl plus C3CON or the NH2 or the CONO2 minus. तो nucleophiles HF minus C2H5O minus C3 or NH2 minus. These species have the unshared pair of the electrons which can be donated and shared with the electrophile. Electrophiles BF3Cl minus C3CONO2 plus reactive sites have only 6 valence electrons and can accept electron pair from the nucleophile. Problem 12.13, identify the electrophilic center in the following C3CH double bond O, C3CN and C3I. So among the C3CH double bond O, C3C double bond triple bond N and the C3I, the stranded carbon atoms are electrophilic centers as they will have partial positive charge due to the polarity of the bond. Now the electron movement in the organic reaction. The movement of the electrons in the organic reaction can be shown by the curved arrow notation. It shows how change in the bonding occurs due to the electronic redistribution during the reaction. To show the change in the position of a pair of electrons, curved arrow starts from the point from where an electron pair is shifted and it inside a location to which the pair of the electron may move. Presentation of the shifting of the electron pair is given below. So from pi bond to the adjacent bond position or from pi bond to the adjacent atom. फिर इधर से है from the atom to the adjacent bond position. The movement of the single electron is indicated by a single barbed fish hook, that means half-headed a curved arrow, for example in the transfer of the hydroxide ion giving ethanol, and in the dissociation of the chloromethane the movement of the electron using the curved arrow can be depicted as the follows. Now the electron displacement effects in the covalent bond. The electron displacement in an organic molecule may take place either in the ground state under the influence of an atom or a substituent group in the presence of an appropriate attacking reagent. The electron displacement is due to the influence of the atom or the substituent group present in the molecule cause permanent polarization of the bond. Inductive effect and the resonance effects are examples of this type of electron displacement. Temporary electron displacement effects are seen in the molecule when the reagent approaches to attack it. This type of electron displacement is called the electromeric effect or the polarizability effect. In the following section, we will learn about this type of electronic displacement. Inductive effect. When a covalent bond is formed between the atoms of a different electronegativity, the electron density is more towards the more electronegative atom of the bond. Such a shift of the electron density results in a polar covalent bond. Bond polarity leads to the various electronic effects in the organic compounds. Let us consider the chloroethane C3C2Cl, in which the CCl bond is a polar covalent bond. It is polarized in such a way that the carbon 1 gains some positive charge del plus and the chlorine some negative charge del minus. The fractional electronic charge on the two atoms in a polar covalent bonds in a polar covalent bonds are denoted by the symbol delta, and the shift of the electron density is shown by an arrow that points from the del plus to del minus end of the polar bond, del plus to del minus. Now the in turn carbon 1 which have developed partial positive charge draws some electron density towards it from the adjacent CC bond. Consequently some positive charge del develops on the carbon 2 alpha, where del plus symbolizes relatively a smaller positive charge as compared to that on the carbon 1. In other words, the polar CCl bond induces polarity in the adjacent bond. Such polarization of the sigma bond caused by the polarization of the adjacent sigma bond is referred to as the inductive effect. This effect is passed on to the subsequent bonds also, but the effect decreases rapidly as the number of the intervening bonds increases and becomes vanishingly small after 3 bonds. The inductive effect is related to the ability of the substituent to either withdraw or donate electron density to the attached carbon atom. Based on this ability, the substituent can be classified as the electron withdrawing or the electron donating groups relative to the hydrogen. Halogens and the many other groups such as the nitro, cyano, carboxy, ester, aryl oxy, etc. are the electron withdrawing groups. On the other hand, the alkyl groups like the methyl and the ethyl are usually considered as electron donating groups. Now the polar which bond is more polar in the following pairs of the molecules: CH3H, CH3Br, CH3NH2, CH3OH, or the CH3OH, or the CH3FH. So CBr means Br is more electronegative than the HCO and the CO इसमें भी हो जाएगा. So in which CC bond of the C3 C2 C2 Br the inductive effect is expected to be the least. So the magnitude of the inductive effect diminishes as the number of the intervening bonds increases. Hence, the effect is left in the bond between the carbon 3 and the hydrogen. Now, the resonance structure. There are many organic molecules whose behavior cannot be explained by single Lewis structure. An example is that of the benzene, its cyclic structure containing alternating cis single or the phi double bond found inadequate for explaining its characteristic properties. As per the above argumentation, benzene should exhibit two different bond lengths due to cis single and the phi double bonds. However, as determined experimentally, benzene has a uniform cis bond distance of 139 picometer, a value intermediate between the cis single 154 and the phi double 134 picometer bonds. Thus, the structure of the benzene cannot be represented adequately by the above structure. Further, the benzene can be represented equally well by the energetically identical structure 1 and the 2. Therefore, according to the resonance theory unit 4, the actual structure of the benzene cannot be adequately represented by any of these two structures. Rather, it is hybrid of the two structure 1 and the 2 called the resonance structure. The resonance structure, canonical structure, or the contributing structure are the hypothetical and individual do not represent any molecule. They contribute to the actual structure of the in the proportion of their stability. Another example of the resonance is provided by the nitromethane C3NO2, which can be represented by the Lewis structure 1 and the 2. There are two types of the NO bonds in their structure. However, it is known that the two NO bonds of the nitromethane are of the same length intermediate between the NO single bond and a NO double bond. The actual structure of the nitromethane is therefore a resonance hybrid of the two canonical form 1 and the 2. The energy of the actual structure of the molecule, the resonance hybrid, is lower than that of any of the canonical structure. The difference in the energy between the actual structure and the lowest energy resonance structure is called the resonance stabilization energy, or simply the resonance energy. The more the number of the important contributing structure, the more is the resonance energy. Resonance is particularly important when the contributing structure are equivalent in the energy. The following rules are applied while writing the resonance structure. पहला, the resonance structure have the same position of the nuclei and the same number of the unpaired electrons among the resonance structure. The one which has the more number of the covalent bonds of all the atoms with octet of the electrons except the hydrogen, which has a duplet. Less separation of the opposite charge, a negative charge if any on the more negative electronegative atom, a positive charge if any on the more electropositive atom, and more dispersal of the charge is more stable than the others. Now the problem 12.16, I write the resonance structure of the C3COO minus and show the movement of the electrons by the curved arrows. So first write the structure and put unpaired pairs of the valence electrons on the appropriate atoms. Then draw the arrows one at a time, moving the electrons to get the other structure. उसके बाद फिर write the resonance structure of the C2 double bond CHO indicate relative stability of the contributing structure. तो इसका आता है कि most stable, more number of the covalent bonds. Each carbon and oxygen atom has an octet and no separation of the opposite charge. 2. Negative charge on more electronegative atom and positive charge on the more electropositive atom. तीसरा कि does not contribute as oxygen has the positive charge and the carbon has the negative charge, hence least stable. फिर प्रॉब्लम 12.1 में आता है कि explain why the following two of structure 1 and 2 cannot be the major contributors to the real structure of the C3COOCH3। तो solution है कि the two structure are less important contributors as they involve charge separation. Additionally, structure 1 and contains a carbon atom with an incomplete octet. फिर कि resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of the two pi bonds or between the pi bond and a lone pair of the electrons present on an adjacent atom. The effect is transmitted through the chain. There are two types of resonance or the mesomeristic effect designated as the R or the M effect. Now the positive resonance effect plus R effect. In this effect, the transfer of the electrons is away from the atom or the substituent group attached to the conjugated system. This electron displacement makes certain position in the molecule of the high electron density. This effect in the alanine as follow. तो इसमें है इलेक्ट्रॉन गया रिंग के अंदर आया घूमा और फिर इसके ऊपर पॉजिटिव चार्ज आ गया। पॉजिटिव चार्ज यहाँ भी है, यहाँ भी पॉजिटिव चार्ज है, यानी उस एन के ऊपर पॉजिटिव चार्ज आ रहा है। फिर आता है नेगेटिव resonance effect minus R effect. This effect is observed when the transfer of the electron is towards the atom of the substituent group attached to the conjugated system. For example, in the nitrobenzene, this electron displacement can be depicted as कि नाइट्रोबेंजीन में इस तरफ हो रहा है कि यानी टुवार्ड्स जा रहा है, इसलिए एन पर इधर या ओ पर इधर क्या हो रहा है कि बढ़ रहा है। The atom for the substituent group which represents the R plus for the R electron displacement effect are as follow कि R effect halogen OH OR OCOR NH2 NHR NR2 NHCOR देता है और माइनस R effect C double OH CHO C double O bond CN और the NO2 देता है। फिर आता है the presence of the alternate single and the double bond in an open chain or the cyclic system is termed as the conjugated system. These systems often show abnormal behavior. The examples are the 1,3-butadiene, aniline, and the nitrobenzene, etc. In such system, the pi electrons are delocalized and the system develops polarity. Free electromagnetic effect or the E effect. It is temporary effect. The organic compounds having a multiple bonds or double or the triple bonds show this effect in the presence of an attacking reagent only. It is defined as the complete transfer of a shared pair of the pi electrons to one of the atoms joined by a multiple bond on the demand of an attacking reagent. The effect is annulled as soon as the attacking reagent is removed from the domain of the reaction in the represented by the E, and the shifting of the electrons is shown by the curved arrow. There are two different types of the electromagnetic effect. पहला कि positive electromagnetic effect. In this effect, the pi electrons of the multiple bonds are transferred to the atom to which the reagents gets attached. और दूसरा negative electromagnetic effect. In this effect, the pi electrons of the multiple bonds are transferred to the atom to which the attacking reagent does not get attached. For example, when the inductive effect and the electromagnetic effects operate in the opposite directions, the electromagnetic effect predominates. उसके बाद फिर आता है हाइपर कंजुगेशन. हाइपर कंजुगेशन इज ए जनरल स्टेबलाइजिंग इंट्रैक्शन. इट इन्वॉल्व्स delocalization of the pi sigma electron CH bonds of an alkyl group directly attached to an atom of the unsaturated system or to an atom with an unshared p orbital. The sigma orbital of the CH bond of the alkyl group enter into the partial conjugation with the attached unsaturated system or with the unshared p orbital. Hyperconjugation is a permanent effect. To understand the hyperconjugation effect, let us take an example of the C3C2 plus ethyl cation in which the positively charged carbon atom has an empty p orbital. One of the CH bonds of the methyl group can align in the plane of this empty p orbital, and the electrons constituting the CH bond in a plane with this p orbital can be delocalized into the empty p orbital as depicted in the 12.4a. तो हाइपर कंजुगेशन इधर हो गया और CH3H1s बॉन्ड और एम्प्टी 2p कार्बन इधर हो गया. ऑर्बिटल डायग्राम शोइंग द हाइपर कंजुगेशन इन द इथाइल कैटायन दिए हुए. फिर आता है दिस टाइप ऑफ द ओवरलैप स्टेबलाइज द कार्बोकेटायन बिकॉज द इलेक्ट्रॉन डेंसिटी फ्रॉम द एडजेसेंट सिग्मा बॉन्ड हेल्प्स इन डिस्पर्सिंग द पॉजिटिव चार्ज. In general, greater the number of the alkyl group attached to the positively charged carbon atom, the greater is the hyperconjugation interaction and stabilization of the cation. Thus, we have the following relative stability of the carbocation. Now, the Hyperconjugation is also possible in the alkenes and the alkyl arenes. Delocalization of the electrons by the hyperconjugation in the case of the alkenes can be depicted as in the figure 12.4b. Orbital diagram showing the hyperconjugation in the propene. There are various ways of looking at the hyperconjugative effect. One of the ways is to regard CH bond as the possessing partial ionic character due to the reonance. The hyperconjugation may also be regarded as a no bond reonance भी कहते हैं इसको. तो ये हाइपर कंजुगेशन इसमें ऐसे दिखाया हुआ है कि एच यहाँ पर से एच हटा, एच प्लस हटा और यहाँ पर डबल बॉन्ड यहाँ चला गया, यहाँ पर डबल बॉन्ड था, यहाँ पर आ गया. फिर एक एच प्लस ये वाला हटा, फिर डबल बॉन्ड यहाँ पर नहीं है, फिर एक ए वाला हटा, फिर ये वाला हटा था, फिर अभी ये वाला हटा था और फिर इस तरह से हाइपर कंजुगेशन चलेगा. नाउ एक्सप्लेन वाई C3 tertiary tertiary methyl cation is more stable than the C3 या secondary या मतलब primary या methyl is the least stable cation. तो hyperconjugation interaction in the C3C plus is greater than in the C2 plus as in the C3C plus as 9 CH bond. In C3 plus vacant p orbitals is perpendicular to the plane in which the CH bonds lie, hence cannot overlap with it. The C3 plus lacks the hyperconjugative stability. Types of the organic reaction and the mechanism. Organic reaction can be classified into following categories: parallel substitution reactions, addition reactions, elimination reaction, and the rearrangement reaction. We will be studying these reactions in the unit 13 and later in the class 12. Methods. तो ये यहाँ तक है. फिर यहाँ से फिर नए चैप्टर इसको अलग पार्ट में लेते हैं.